So good afternoon, everybody, in theoretical astrophysics program land and lunar planetary laboratory. We have a special guest visiting on a whirlwind US tour coming from the DPS meeting in San Antonio via University of Washington and now here in lunar planetary laboratory. Thomas Meier, he's a, I guess, finishing PhD student, fourth year.
Yeah, so I still have like 2 years.
About 2 years left if you want to put some ideas in his head. Now's a good chance. Thomas Meier is a PhD student of Joachim Stadl at University of Zurich, who has been really instrumental in developing a lot of the high-performance SPH methods over the years. And he's part of the computational physics group at University of Zurich. And today, Thomas is going to speak to us on towards ultra-high resolution simulations of giant impacts, which is probably going to summarize a number of the recent papers that he's published on origin of Mercury, origin of the moon, and other mysteries. So take it away.
Yeah, thanks for the introduction. So as he said, I'm going to talk about our way towards ultra-high resolution simulations of giant impacts and why we even want to do that. Yeah, now it's always the same. To here first. So why are we doing any of what we are doing? So giant impacts are the last stage of planet formation. Here, an artist's impression of this. Like in the last stages, you only have a few protoplanets left that then impact one another to create the final state of the planetary system. And they play a key role in determining many of the aspects of the finished system, like structure, how many planets are there, what are their masses, what are their compositions, and do they have moons? And as we all know, sadly, we cannot study that in a laboratory because, yeah, the planets. And when we look at the sky, we only see snapshots. We see either a protoplanetary disk or a fully formed system. We do not see this stage. It's really highly unlikely to ever get an observation of such a phenomenon. And that's why we study it with simulations. And the way we do that is we solve the Euler equations with a method called smooth particle hydrodynamics. And for that, we have essentially a point cloud sampling the fluid, and then to build the equations that we solve, we look at a given particle and smooth the values of the state values of the surrounding particles to get the value at the point we are working currently on. And then we can build our equations, calculate time derivatives, and evolve the system forward in time. And this method, the SPH method, is Lagrangian, which means that the state variables, they live on these particles and transported with the flow. And this gives us the ability to model really large deformations. And we can also track the origin of material. So when we are finished with the simulation and look at the end state, we know where did every of these particles come from. So we can, for example, figure out where did the material in a proto-lunar disk, for example, come from. Did it come from the proto-Earth, or did it come from the impactor? And this allows us to analyze the composition of this disk. And the tool we used to do that is called Gasoline. It was developed by Watzley in 2004 and is based on PKD graph, the original PKD graph developed by Joachim Stadl in the 2000s to do cosmology, essentially. And this code was then adapted to really do these planet scale collision simulations by Christian Reinhardt, mostly by adding an interface and surface correction, which I will explain later a bit, and ISPH, which I will also touch later again, and by me during my bachelor thesis, I added a generalized equation of state interface that allows us to use all types of equation of state that we want. And this is essentially our path to our decision that we need a new code to be able to continue with this work. So as I said, I first started working that during my bachelor thesis in 2020, where I added this EOS lib, as it's called, this layer between the SPH code and the different equation of state codes. And then we had, with that, we made a paper called the EOS Resolution Conspiracy, Convergence in Protoplanetary Collision Simulations. And based on what we learned there, we then studied iron-rich planets, the formation of iron-rich planets via giant impacts. And we also have these two upcoming papers about the moon forming that were also done with gasoline, but those I won't talk about because they don't really contribute to the path to high resolution. And then I started developing a new code called PKD-Graph3. So that is based, like the SPH implementation there is based on PKD-Graph3 as it was, the cosmology code, pure gravity code to do dark matter simulations. And yeah, I added ideal gas SPH into this code as part of my master thesis in 2021. And now in last year, I started my PhD and continued working on this code to enable what I will show later, these simulations of giant impacts. And we have several publications in preparation, which I won't talk about because yeah, we'll see that at some point. So going back to gasoline again. So we were studying collisions between differentiated protoplanets with this weird mass of 0.5 to 5 Earth masses, which some people may know what it means. That there was a preliminary study to do moon forming simulations, because two times this gives exactly the mass that you need for that. And we compared the effect of the equation of state in these kinds of simulations. We compared the Tillotson equation of state to a more modern, more physical equation of state, the Aneos equation of state. And we used bodies that had were fully differentiated with 33% iron core and 67% rocky mantle, where we used dunite for Aneos and granite for Tillotson. And we studied different orientation of these spinning bodies. We had spinning bodies, and then the orbit gives you essentially the orientation of your system. Like the two bodies, they collide like this, and it gives you a spin orbit in this direction. And then spinning planets can then be oriented either in the same direction or in the counter direction, which is then called like up is both bodies are spinning in the same direction as the orbit, and then down is they are spinning, both bodies are spinning counter rotating to the orbit, or then down up is then one is spinning with and the other one is spinning against it, and NR is we call it non-rotating.
And these are all in the plane.
Yeah, that's all in the plane, because otherwise you just like explode your parameter space. It gets just untractable at that point. And yeah, what we did was we measured the rotation period of the end product of these collisions. And we saw in red the results from Tillotson and in blue the results from Aneos, depending on the resolution of the simulation, the number of particles in the simulation. And we see that in Tillotson, with Tillotson, it takes a long time to converge, or like this one hasn't even converged at all. Right? While the Aneos results, sometimes they are like don't change at all, like this one, or then they converge around 100,000 particles. And the reason for that is that the way these two equations of state treat the gaseous phase, like the low density vapor phase. And the more realistic one, the NS one, treats this phase much more correct, so that in the end product, most of the end body was condensed, while in the Tillotson case, a lot of the mantle was still considered gas, and so was interacting with the disk that formed to transport out a lot of angular momentum. And this is this means that at low resolution, a lot of angular momentum was transported away, slowing down the planet. And then if you go up with the resolution, the effect of this angular momentum transport gets smaller, which means that the planets then kept rotating faster. So we have seen that, yeah, even this, like the most fundamental result, it depends on the resolution if your equation of state is bad. And then we also measured QRD star that in head-on collisions, which I explain now. QRD star is the specific energy that you need to unbind 50% of the total mass in your collision. It's, yeah, at that point you destroy half of your system. And what we have seen here is that, as found in the literature with Tillotson, the value just keeps going down with resolution. Here it's a weird x-axis. It's essentially number of particles to the -1/3, which means that resolution increases in this direction. So, and 0 means that there's infinite particles. Right? So we see that it just keeps scaling. Whereas with anions, at a certain point, it stops going down, so it converges. And we found the reason for that, again, in the equation of state. Once we start to resolve a given feature, in this case, this ring that is formed by the iron cores that collide, they form this ring, and then it collapses again. And once the resolution is high enough to resolve this feature, the value of QRD star doesn't change anymore. And this is not found in Tillotson. And the reason for that is, again, the vapor phase of the equation of state, which has a more physical modeling in anions, modeling this ring. And yeah, based on that, oops, sorry, there's like a volume knob here, and if I press it, it unmutes me. So based on that, we then made a second publication where we studied the formation of iron-rich planets via giant impacts. So there was a growing number of exoplanets found that are similar-ish to Mercury in the sense that they have a high iron content, meaning they probably have not been formed by just pebble accretion or whatever, because in that case you would accrete like Earth-like composition. And so the theory there is that, yeah, there was a giant impact that stripped parts of the mantle away to leave then a highly iron-enriched body. And so we studied head-on collisions between differentiated bodies between 1 and 10 Earth masses, with now an even more advanced equation of state, the M-anios equation of state, that is even more physical in the vapor phase and the liquid phase. And we use 30% iron and 70% phosphorite bodies. And we derived scaling laws again for this QRD star value that is needed, and for the fragment mass as a function of QR over QRD star. And here we found that the dotted line is what was used in literature before. And we found that at these high masses of colliding bodies, it's not applicable anymore because it was developed using small body simulations, rubble pile simulations and asteroid-sized bodies. And we found that, yeah, we have, like here there's more mass at low specific impact energies, but then here at some point we then lose rapidly lose mass. And we did the same then for the iron mass fraction, which again, here in this region we are close enough to the literature, but then at high specific impact energies, we get again this rapid loss of mantle. And by combining these scaling laws, we were then able to create this figure where we essentially have on the x-axis the fragment mass, like what the mass of the exoplanet you're looking at is, and on the y-axis we have the iron mass fraction, and in these shaded gray regions we see what is theoretically possible to generate by a giant impact. And there are two shaded regions, one where we say here the target could be between 0.1 and 10 Earth masses, and the impact velocity is between 20 and 100 kilometers per second. And in that case, we can only form like planets in this region here. So these ones, they need higher impact velocities to form such high iron contents. And we then made a second shaded region with 160 kilometers per second. There then all the planets are then in there, at least like the most likely value, because this part of the error bar we cannot hit. And we then transferred that into the fragment radius via internal models, and we see, yeah, we can hit all of them. So we could, in theory, explain all these high iron content exoplanets with a giant impact, depending on how realistic these impact velocities are, because that depends on the system, right? If you have close-in planets where the Kepler velocities are high, it could be, but it's probably unlikely. But it's not our job to say that. It's job of those people that are analyzing the specific systems. We are essentially providing a tool to say, yeah, it's likely or not to happen. But here again, we learned that we need this equation of state, because if you apply just some scaling laws that you formed with, like, I don't know, Tillotson on asteroid-sized bodies and apply that to 10 Earth mass exoplanets, you're probably wrong. And yeah, so at that point we then try to figure out how can we proceed from here. So one point we certainly know now is that we need advanced equation of state, right? Because if you use Tillotson in this regime, you're probably wrong. So that means going forward, we want to keep using this modern realistic equation of state. But we also learned that the resolution is very important. Even though some observables converge quite fast with a realistic equation of state, others do not. That I haven't shown that, but others do not. Like the bound mass does not converge as fast as the rotation period. And also, what is even more interesting, we cannot resolve low mass structures. We discussed before in the car, early SPH simulations, they didn't have the resolution to even resolve crusts. But we cannot do that at this point still, right? But right, so low mass structures like this, crusts, oceans, atmospheres, you cannot do that with 100,000, 200,000 particles. You need millions or billions, as you will see. And yeah, so we need more particles. But we cannot do that with gasoline, because gasoline is old and it doesn't use modern computer features, and it doesn't scale well. So we decided, yeah, we do something new. And one aspect that the new code also can help you with, if you decide to do not go to high resolution, you can do low resolution simulations, but like thousands of them, right? Which is also not really possible with the old code that we're using. We can do a few thousand, but that's then like a huge endeavor. So yeah, we need a new code. So I did that. And what I did is I used this code PKD Graph 3 that was developed based on Joachim's like whole career, and was then the newest state was developed by Doug Potter in 2017 as a cosmology code to do dark matter simulations. And the biggest run they did was 8 trillion particles on Titan, I think, yeah, the Titan supercomputer. And yeah, so I used it because it scales well. And I added SPH implementation to that, fully conservative, self-consistent SPH with grad H terms based on Springer and Hörnquist. And SPH, I come now back how SPH works. You have your particle cloud, and you want to calculate your density, which is needed for the next steps of the calculation. And how you do that is you sum the mass of each particle in the kernel weighted by the kernel function with the distance between the particles and the kernel size. And then you can calculate like velocity derivatives, again with the mass, and then here with the density and the pressure and kernel derivative. And you can do the same then for the energy. But these equations, they are valid if H is constant. But that is not very clever to use a constant H, because then if you have a system that is changing in length scale rapidly, like in collision of planets, you're then not resolving either the big scales or the small scales. So you need a correction, and this correction is this term here, which also again contains the derivative of the kernel. And yeah, this correction then goes in at certain points. But for this correction to be valid, you cannot just choose the H as you want. You have to satisfy this constraint here. So this means the mass inside the kernel of a particle has to remain constant. So if the density of the particle goes down, you have to increase the kernel size, and the other way around. And this means doing Newton-Raphson iterations during the density calculation. And yeah, that takes a lot of time to do that. But the way, well, yeah, this slide uses a lot of computation, this slide. Sorry. Yeah, so the way I did it is faster than the old way for even doing a simple density calculation. So that the old way was just, yeah, it was looking at the particle and searching for all the neighbors and calculating their interaction. And the way I do it, I explain a bit later, but it is essentially so fast that I can do the Newton-Raphson iterations, and I'm still faster than the old way of density calculation. Okay, then I also added this interface and surface correction that I alluded to before. This is based on Ruiz Bonilla, which in turn is based on the work of Christian Reinhardt. So we are like doing a detour of a different author. And what this is doing is, here is the profile of an Earth model, right? You have the core and the mantle, and at this point you have these two layers of particles. They have wrong densities because you're essentially smoothing over this layer, and this layer for these particles, and the same for this one, right? You use this layer, this layer, and you get a wrong density. And this leads then to wrong pressures, because you have this wrong density. You ask the equation of state, yeah, what's my pressure here? And you get this, and this leads to essentially you separate the layers between the core and the mantle, and then, yeah, the method is then not very good at that point. And so this correction is essentially corrects us this layer up here, right? In orange or whatever red is the corrected state, and this is now okay, right? And the same is here at the surface. You also have this wrong density, and we correct it up so that we get a correct density again, and yeah, correct simulation at that point. And we also have this ISPH, which means that we do outside of shocks, we perfectly conserve entropy with a trick. Here is an example of that. So this is essentially you have, without gravity, you just have a cube of particles that has no self-gravity and only pressure, so it will expand, right? And due to numerical errors, you get that, right? You start here, and in theory, it should evolve along the black line, but due to numerical errors, you get this spreading of the particles, essentially. And with the correction, we get this result where they follow the isentrope much closer. And so we do this outside of shocks and get very nice results with them.
What are the colors?
Different time steps. So yes, yeah. So essentially, you start here, and then you get the green result, and then the blue result, and then the red result. And you see in the end state, essentially here a few particles that are essentially out away from the isentrope by numerical errors. Yeah, and so I added that to the new code also, so that we can use this. And then I added the generalized equation of state interface that I developed in my bachelor thesis. And the code uses a kick leapfrog scheme with an embedded predictor corrector scheme for the velocities that are used in the SPH formulation. And this is essentially taken directly from the cosmology code. And yeah. Now, we are really fast, right? That's the whole point about that. And the way we do this is we use, for gravity, we use the fast multipole method, which gives us an order n time complexity, which means that doubling the number of particles means doing twice the work. And that is the best you can achieve in gravity. There's no way to get any faster than that. But we can improve the runtime further by using SIMD. It's a, what's that? Simultaneous instruction, multiple data, whatever. Yeah, you essentially do the same instruction on a full vector of values, and speed up the calculation by essentially the vector width factor. And we also use GPU to further improve the performance. We just offload a lot of the calculations to the GPU. And the most computationally heavy part of SPH is finding the neighbors. Which particles do I have to use to calculate my time derivatives? And I tightly coupled it to the fast multiple tree code in a way that speeds things up. So we essentially have like a group of particles that live in here. We have like the boundary, the bounds of their positions. They also have a bound of their kernel sizes. So, which means that any particle outside of the black line cannot be a neighbor of the particles that are in here because they are too far away. And that means I can, while finding neighbors, I can ignore everything that is outside the black box. That means this cell of 16 particles here, do not have to look at them. These ones, also, can just ignore them. But these ones, I add to a list of particles that I think could maybe be neighbors. They don't have to, but maybe they are. And these ones too. And then at the end, when I walk the whole tree, I have a list of particles that may be neighbors of the particles in here. And then I ship essentially these particles and the list of neighbors, of potential neighbors, to the GPU and tell the GPU, do SPH with that, and then continue to the next group that is then probably here, and do the same again. And this speeds up the process a lot because we do neighbor finding a factor of amount of particles that are in here less times. Right? I do in like only one tree walk per 64 particles instead of one tree walk for every particle. And this is much faster. And this also gives us order n scaling for the full substep, like gravity, like density and gravity and SPH forces together, scale with order n. But as we discussed during lunch, we scale with n to the 1/3 with the amount of steps that we have to do. Right? And so this means that our full method scales with n to the 4/3, and that is exactly what we see here. We have in red we have the n to the 4/3 scaling, and in blue we have measured on supercomputer the scaling of the method up to 1 billion particles. We scale exactly as it should. There is no way to scale better than this. And then we measured parallel performance on this supercomputer here. That's in Switzerland. It has CPU nodes and it has GPU nodes, which I will show on the next slide. And yeah, at 8 million particles, we scale to, I don't know, 16 nodes. But then at 1 billion particles, we scale up to 256 nodes. And each of these nodes has 36 cores. So we scale to a lot of cores. I'm so bad at it. But the best thing about all of this is the comparison to gasoline. So on one node, we get a speed up of between like 3 and 5, which is okay. But then comparing best result to best result between gasoline and the new code, we get at 128 million particles, we get like a speed up of 45. That's not 45%. That's a factor of 45. And at greater than 50% efficiency, which is what you, if you write proposal to a supercomputing center, they tell you, yeah, you cannot use more nodes than gives you 50% efficiency. And at that point, we get even to like 65 factor of speed up compared to gasoline. And that means that what simulation that took 2 months with gasoline takes a day with the new code. And that helps a lot when doing studies of giant impact. And then in the beginning of summer, I added GPU support to SPH, which means that most of the floating point operations of the SPH code can now be shipped to the GPU, which means that the CPU is free to do the tree walk, right? To finding the neighbors. And these nodes, they have only 12 cores plus a GPU. And here we scale to, at least 512 nodes. Very good. This is the run with 1 billion particles. And and at this point, at 256 nodes, we're still like at 60% efficiency. So that means if we propose for a project, we can run at this node count our simulations, which means they take a few weeks at 1 billion particles. It wasn't even like thinkable with old code. So this slide I added on Sunday. And validation is difficult. What we have done is we've extensively compared the results of the new code to gasoline with ideal gas and with the fancy equation of state. And we compared to simulations in the literature, which I will then show some videos afterwards. And we had a bachelor student to shock tube test with the new code, and it might look like it's smearing a lot, but that's a bit there are only 32 particles in this direction. It looks like more, but they are all like in the Y and C direction to get the 3D kernel. So it was done in fully 3D. So, but in this direction, we only have 32 particles. Quite okay. And even, especially this pressure blip here it's impossible to remove it, but it is quite small for the resolution that we have. And we suspect mostly because of the correction terms. And he also did a set of explosion tests, which is essentially like you have a cube of thin gas, and then you set off a supernova in the center, and you look how the shock moves. And in blue are our particles, and it really the most important thing is that the peak is at the correct position, and it is. So we are really happy with that. But that's essentially all the validation we have done until now. We will do more so that we can publish it, but that's where we are at currently. So now the examples I promised. Right. So Mercury is weird. Mercury has too much iron, essentially. So the hypothesis there is, as I already alluded to, is there's a giant impact that stripped away parts of the mantle, leaving a highly enriched body. And this is a simulation of that. It's 150 million particles are in this simulation with 2.25 mercury masses target and 1.125 mercury masses impactor. And they collide. Oh no, it's on my laptop it's really smooth, but here it's that's zoom, right? This is not really sad.
Maybe when you replay it, it'll be smoother.
No, it's on my laptop. It's perfectly smooth.
Oh, Zoom's just picking every.
Yes.
You have sharing options with video enabled?
Where would that be?
So there's a green bar at the top. So share with can you press share again? So something like with video optimization that might change.
That might help. Yeah, but now it's pixelated as
Yes. And does it work?
No, it's even worse.
Yeah, it's definitely worse. Okay, well,
Yep,
Thanks, Tim.
that didn't help.
sorry.
Let me undo that. Yeah. Yeah, so I have screenshots afterwards. Sorry.
And these are all clumps. Those are not individual particles. Those are actual.
Let me play it again, sorry. It's now really confused.
Yeah, it's working.
Yeah, there are like hundreds of particles in these clumps here.
Yeah, those are actually sort of quasi-resolved objects. Yeah,
Yeah.
wow, that's fascinating.
Yeah, let me go to the next slide. And yeah, I have snapshots after 3.5 hours, and they look like this at 300,000 particles. That's what we know, right? We have particles here and some lonely particles out here. But then if we go up with the resolution, takes a second to update. Yeah. Oh. So this is at 75 million. And then here we are at 150 million. And what we see here is, yeah, maybe a lot of like turbulence in the core, and like all these small bodies in the infalling material that you just don't have at like this resolution. You just don't see that, right? Sorry, I quickly unsure and share again. Maybe then it picks up a bit. Yeah, not really. Yeah. Yeah, sorry, I wasn't prepared to do this over Zoom like this, that even at least those that are in the room can get like a fluid motion. Yes. So yeah. So with increasing resolution, we get much more substructure here, and like the turbulence in the core that is not there at low resolution. And then I have a second example, collision between two Earth analogs. Looks like this, with one Earth, another one. And on the left side, you have again the same style of figure as before. Like it's a projection of the density. Like what you see is like the maximum value in this direction. And on this side, with a slice through the center of the simulation, and like really a thin slice, so that we can see more of the structure there. And this is a bit better now. So you see this arms that form here. This suspended core material in the mantle that you can see at this resolution. So this is at, what was it, 200 million. It just keeps spinning now. And what you, these blobs here, essentially like these small masses here that are then just spread over their kernel size. Yeah, and again, here a snapshot after 5.3 hours of the impact. And at 200,000 particles, we get this blob, this formless blob. And if we increase the resolution now to 2 million, we start to get these features here of these arms. And they take away some of the angular momentum. which can be seen like here that the core is like here, and here at high resolution it hasn't rotated as much yet, because some of the angular momentum is now in these arms instead of in the in the core. And then if we go to more resolution, the arms get more pronounced, and we get more turbulence in the core, more of this submerged core material in the mantle. And this is 20 million. Then this is from the video you saw before, 200 million. Now we have really pronounced arms, and here you can see a lot of these flakes of suspended material. And then we go again, 10 times more particles, and now these are now really pronounced, these arms. And here you can't even see the flakes anymore because there are so many of them. Yeah, that's essentially what I want to say. The arms get more pronounced, and the core material is mixed more and more into the mantle. And this also has a visible impact on the core rotation, as I said before. But also, it's a bit hard to see, but the initial conditions is completely symmetric, right? And so if you look at this result here, this is completely symmetric. And here we still are pretty much symmetric. But here we already start to see that it's not as symmetric anymore. And that's turbulence, right? Once you start to resolve the turbulence, you get chaotic motion. And at this point of resolution at 2 billion particles, we already lost so much of the symmetry that the core doesn't even look symmetric anymore. And it's just because during the infall of the initial arms that form, it gets disturbed on this side, gets much more disturbed than the other side, just because of the turbulence. And here is the same thing again. Here we have 200,000 and here 20 million. And this is a short clip, and it stops exactly at the correct position. Maybe here. There's this feature here, where some small amount of material is ejected. And this is completely absent at low resolution. And yeah, so I saw that and thought, what is that? What kind of weird bug is this? And turns out it's not a bug. It's actually a feature. And so at this point of with this resolution 200,000, you don't see any of that. Then here you start to slowly see it here, but you still don't know why is that. And then if you go up with the resolution, it gets more pronounced. And you start to understand what is happening. There are these two shock waves that are like traveling through the body, and they collide essentially. This one is coming from this direction, this one is coming from here, and it shoots out a little bit of material in this direction. And so at lowest resolution, it's not even there. And to really understand what's happening, you need quite a lot of resolution to, in the figures, see the shock waves that are causing the outcropping of the material. Yeah. And here now, sadly, is again like this video that is now going to happen at like 0.5 frames per second or something. This is 2 billion particles. That's the highest resolution that we've done. And you see, yeah, we lose the symmetry, that the arms, they're there, but they don't look symmetric anymore. And here is now the full glory of high resolution simulation in high resolution image. This is a snapshot of the video you just saw before. And you see like all these tiny features here, like this looks just phenomenal here. And this low pressure region that crops out when the cores separate again. Just so many features everywhere. I'm so happy about this thing.
I have a quick question.
Yeah.
What do you do with negative pressure? Do you set it to 0?
Yes.
Okay.
Yeah. So at this type, in this type of simulation, they are actually negligible and only lead to like problems. So we set them to 0, but it's a good question, right? So if you have small bodies, it starts to matter at some point. And here is
sorry, can I ask what the color scale is again?
Oh, sorry. Yeah, the colors are density, and they range between, like, here's 0 outside here, and this was 14 or 15 grams per cubic centimeter. I don't know what this is in freedom units. Freedom units. Yeah.
Yeah, we do grams per centimeter cubed. But what is so what's happening inside of the core, like the center of the body? Why do you have low density blue, but also what highest density is white? Or what is
no, red is the highest density.
So what is white?
White is around 7.
Oh, okay, that's the middle. Okay.
Yeah.
Okay, yeah, you're doing blue, white, red.
Yeah,
is
blue,
the-
white, red.
is the color bar. Okay.
Yeah, here is the end figure from the video again, just in high resolution. Yeah, and it's just all these tiny flakes of core material that are suspended. You don't have that at low resolution. And here is the same thing in temperature. It goes from 0 to like, I don't know, like 100,000 Kelvin. So you get really superheated, low density gas outside here. Like this is like, yeah, gas form rock. This is just super hot. And yeah, it's a bit hard to see on the zoom, but there's like so many little structures in here. I can show you on the laptop afterwards. Yeah. And with that, I come to my summary and outlook. So as we've seen, the equation of state has a large impact on simulation results. So we really want to use these modern equations of state. And high resolution is also important to resolve low mass structures. And as we've just seen at the end, some features only appear at high resolution. They're just absent at low resolution. And yeah, the new code provides both. We have the equations of state and we have the resolution. And now the question is, what do we do now? So next steps is obviously produce some actual physics, like some actual papers that are like planetary science papers. But then we also want to work on the code. We want to add state-of-the-art artificial viscosity limiters. So we are not limited to like 7 days maximum for disk evolution, but we can then do longer simulations. And also we want to add artificial thermal conductivity, which should help in mixing, because it reduces the artificial surface tension between phases. And the most important one is material strength. We know that for lower mass objects like, say, Pluto or even Mars, and then asteroids especially, material strength becomes dominant. You cannot then say anything reasonable without material strength. And so we are working with another group at Bern, which you know them, to incorporate the material strength formulation into the code. And preliminary thoughts lead us to the conclusion that adding this will not change the performance of the code. At least not if we are running on GPU, because as it is now, when we run on GPU nodes, we do not fully utilize the GPU. So we are communication limited. And this means that once we have the strength, we just increase the usage of the GPU, while the full loop runs at the same speed. You just use more of the GPU to do the strength calculations. And that would mean that we can do billion particle simulations of Pluto, say. And that would really help in all of the physics. And with that, at the end, I have some more videos, but as we've seen, it's a bit hard over Zoom, but maybe I can show it anyway. So this one is, yeah, you should know this. It's again, Mercury. It's like a hit and run scenario where we have, like, this is much larger than Mercury, and this one is even more larger than Mercury. And when they collide, they give us a Mercury at the end. And yeah, it's no. It's so sad. Yeah, we get these balls that are just taking forever to fall in again. And sometimes they even collide in mid falling.
Too high resolution
Why?
for the internet,
No, it's just assumed, just won't
Yeah.
give you more
but
frames.
it is limited by the resolution of the image. Yeah, we need to take closer looks at this.
Yeah. And here is something that I'm currently working on. So there's a proto-Jupiter, like slightly below Jupiter mass, fully formed, like with a rocky core, ice mantle, and hydrogen helium atmosphere. And the impactor is 10 Earth masses, again, rock core, ice mantle, and hydrogen helium atmosphere. And they collide. You have this shockwave that travels around the planet multiple times. Yeah, well, after the talk, you can view it on my laptop.
Yeah.
And it's the same thing again in temperature, which is, this is a slice again. And here I want to actually pause this maybe here. And if you look here, this region, all the turbulence that we get here would just not be resolved in low resolution simulation. Yeah, and with that, I end my talk. Thanks for your attention.
Wow. Of course, a number of questions. I know we'll get to talk more. One more, I think, one comment on the value and importance of strength beyond just the smaller collisions, like Pluto smaller than the Earth, Mars even for the Earth, especially at this resolution. If we're going to focus on these new features that are visible now, the turbulence, the mixing, if we're going to actually focus on that, even at Earth scale, strength is going to make a difference as to where that turbulence is occurring or where the mixing is occurring. So as we get into this ultra high resolution framework, missing strength and still trying to make or reports on such fine resolution detail like turbulence, I think I don't think you can talk about this without having that detail on top of it. Or I mean, you can talk about it, but I suspect it will have an important effect even at the Earth and maybe not Jupiter scale, but maybe.
I mean, certainly not in Jupiter
Jupiter
scale.
is all fluid anyway.
There's no
Well, until you have the surface of the core there.
Yeah, but it's then so hot. It's
Maybe.
But yeah, you're right. That's we have to look at that. Well, once we have the strength, we have to compare. That's true.
So I have about 10 questions, but I don't know which one to ask, but I was curious about your EOS interface module. So can you just give like a little short synopsis how that works? Like, let's say I have you might know about this aqua equation of state or some of this, but like I have some equation of state. How does that work?
So essentially you write a small C module that provides calls that give you, for example, pressure of temperature and or pressure of density and internal energy. And you write a bunch of them, and then you add in the equation of state library, the EOS lib, you essentially add small calls where you then call this external library, and they are all guarded with if-defs, so that the code, the PKD graph code, can be compiled in complete absence of all equation of state libraries.
Oh, okay.
And then if you then add, like if you have the EOS lib repository on your machine and compile, then it compiles that one in. But if you don't have the Tillotson library and the iOS library, then you cannot, it compiles, but you can then just not use those sub-libraries, let's call it that. And so it's all guarded, and so you can compile at any combination of equation of state. And so to add a new one, you essentially have just to add some lines that call your external functions.
And for your bachelor's dissertation, did you write? You said you write like a new EOS generalized EOS equation, or
Oh, no, that was, it's not an equation of state. It's like this.
It was the interface.
The interface that handles, like, it exposes some functions to the SPH code.
Okay.
Which take like a material number and whatever, like density and internal energy, and return pressure, let's say.
Okay.
And so the SPH code, gasoline or PKD graph, it doesn't have to know anything about the underlying equation of state. It just calls this library, gives it a material number that's a certain integer, and tells it, yeah, give me that. I give you.
So for all of these simulations, you've been using MNEOS equation of state, and then interfacing through your library.
Yeah.
Okay.
Yeah. Yeah. So this simulation, for example, it uses MNEOS for the core, ANEOS for the mantle, and RIOS 3 for the hydrogen helium. So.
Okay. So is that also a new and like kind of powerful technique of your interface that you can use multiple different? Eric, I don't know if we can do this with our code. Can we access multiple different equation of states? Like,
Oh, yeah.
okay, at the same time. Okay. All right, cool. But it's so.
Well, actually, I'm not sure if it's set up to do that, but I mean, in principle, we could. It's
But yeah, but your interface is set up to take in multiple different.
Yeah, exactly.
Cool.
Yeah.
So I have a more sciencey question. If you the origin of Mercury simulation is pretty interesting, because in low resolution SPH, you don't get these discrete clumps of basically new little planets. And you know, I think your technique has a lot of potential to rule things in or out, because if you form Mercury in a certain way, at low resolution, you just get this cloud of debris, and you say, well, that stuff's going to be a disk of dust or something, and you might be able to say it goes away, or it spirals into the sun or something. But if you're forming discrete objects that are, you know, the size of Vesta or something, and you're forming hundreds of these, you could probably, through orbital dynamics, maybe determine that some of these should be there now, and they're not. Not to pick on Mercury specifically, but I think a number of the problems that we think of now need to be looked at in more attention to survivors of the collisions.
Yeah, that's true. When I first started working on Mercury, I asked Christian, what happens to the stuff that we eject? And he said, yeah, no one is talking about that. But yeah, you're right. At the point where it was just a gas cloud, the argument is, yeah, it was like blown away by solar wind or whatever.
Yeah.
But if you really form these bodies, that is something we have to look into. Yeah, that's true.
Online, Andrew, you didn't.
Yeah. Yeah, I can see that. Yeah.
Oh yeah, hi, thanks. Yeah, thanks for doing this talk online as well. So, sorry, a bit of a naive question. So obviously these equations of state are, you're having to do lots of phase transitions between, I guess, vapor and liquid and even solid. And I guess I'm just curious, I don't usually think of solids having an equation of state. Are there any particular issues there, or, and just in general of using SPH and doing sort of fluid modeling of something that you might think of normally as a solid?
Yeah, so the idea there is that under enough pressure, even solid acts as a fluid, right? That's essentially the theory behind all what I have been doing until now. So if you enact enough pressure, even rock is liquid. But
So
as
it's not really a phase transition between liquid and solid then in these models?
so the equation of state provides a phase transition there where it that has a jump in internal energy and stuff like that, but it's not like the code treats the material as a liquid in all stages, which is maybe wrong. Certainly, if you look at Pluto, it's wrong, but at these scales, it is correct enough to make some predictions, and that's essentially what we are doing.
So would you say that there's a limitation there if you were to go to, say, for instance, like very low mass bodies, or not giant impacts, like
Yes,
asteroids?
for example, if you look at cratering, you cannot do that with our code yet, right? Because if you have a Mercury and throw an asteroid at it, it will create the impact. It will simulate correctly, more or less, but then the crater will go away because it's a liquid. It will just get round again. And so for that, you need what I mentioned in the outlook, the strength model, to model that correctly. Yeah.
And then if I can, is it okay if I ask one more quick, hopefully quick, so I gather that, I mean, I know PKD grav is used for many different things in both astrophysics and planetary science. So is PKD grav itself basically just n body, and then all these equations of state add-ons are done separately? And then, for instance, when Derek Richardson does he's got different modules that he adds on. Is that just trying to understand the ecosystem of PKD grav?
I don't understand the ecosystem of Derek Richardson's side, because
well, so he does collision simulations as well, but I gather they're done in a different way, right? Is it the same code that's being used, or is it?
I don't think so, because we have never. I have never corresponded with him about that, and I think, if I understand correctly, his work is based on the original PKD graph and not PKD graph 3.
That's right.
So he probably has not access to the FMM, like the fast multipole method there, and he also probably has not access to the GPU part of the new code. So I don't know exactly what he is doing. I think that it was a spin-off of a quite old version of PKD graph. But my part of it is, it's all in the general PKD graph 3 repository. So you can just go there and download it and compile and run. You probably won't understand what you have to do to make it run, probably, because documentation is not really there yet. But you could, it's all open source. And the equation of state libraries, so that the intermediate layer is open source, the Anios module is open source, the Tillotson module is not, I think, because we are not using that currently. And then we have the Rios 3 one, which is also not open source yet, and then we have SCVH, and that's also not open source. But in theory, you can add them quite quickly, and as I said, you can compile without any of them. So,
sure. Thanks.
Answer your question. I don't know.
Yeah. No, that's helpful, thanks.
I had a question related to slide 13, and I don't remember what the question was, but I remember the slide number.
Let's see.
Yeah, so I can go back to slide 13, maybe. Which one was 13? Wait, sorry, this is no, just sorry. I think there's an easier way to do that. This is slide.
Maybe it was slide 17. Yeah, oh yeah, oh, I guess I did get to ask my question. Okay, because that was related to the generalized equation state interface. Well, does anybody else have a question for Thomas? If not, let's thank our speaker again. And then I think since we have this room, you want to plug into the HDMI and show your movies in full glory,
Yeah, let's try that.
straight from your laptop?